In this lesson, you're going to learn the factor theorem, and you're finally going to learn how to factor a polynomial function that is degree 3 or greater. Part 1 of this lesson, I put in just a reminder about the remainder theorem. So remember, the remainder theorem tells you that if you wanted to figure out what the remainder would be if you're dividing two polynomials, all you have to do is plug the 0 of the divisor, so what makes that divisor be 0 would be -2, into the dividend, and whatever the value is, that would be the remainder if you were to divide them. So if I want the remainder, when this function is divided by x plus 2, I would just plug in -2 for x into the dividend and evaluate it. So I'd have -2 cubed plus 4 times -2 squared plus -2 minus 6. This would be -8 plus 16 minus 2 minus 6, so minus 8, and this gives me 0. So what we just figured out here is that x plus 2 divides perfectly evenly into that dividend. In fact, it's a factor of it because there's no remainder. So if I were to divide this x cubed function by x plus 2, I would get a quotient that is also a factor of the dividend, meaning I could write this dividend in factored form by writing it as the product of the divisor and the quotient. The tricky part of today is being able to figure out, okay, well, what should I divide the polynomial by so that I get a remainder of 0? That way I can put it into factored form. And that's what I'll take you through. Part B says, verify our answer by completing division using long division or synthetic division. Well, since the divisor is degree 1 with a leading coefficient of 1, I think synthetic division is quickest. So let's do the synthetic division. 0 of the divisor goes here, and then coefficients of the dividend go here. And in the dividend, I had degree 3, 2, 1, 0, so all degrees were represented, so I didn't need to put any 0 placeholders. And now I will do the synthetic division by bringing down the first term, multiplying it by the 0 of the divisor. -2 times 1 is -2. 4 plus -2 is 2. -2 times 2 is -4. 1 plus -4 is -3. -2 times -3 is 6. -6 plus 6, 0. So remember, this is the remainder. This is the x to the 0. This is x. This is x squared. So I just verified that yes, in fact, it does have a remainder of 0. Just to drive home the point that I want you to understand here, let me rewrite the dividend, x cubed plus 4x squared plus x minus 6, as a product of the divisor, x plus 2, and its quotient, x squared plus 2x minus 3. And then I would also have to do plus the remainder, but since the remainder is 0, look what we were able to do. We were able to get this polynomial, the dividend, into factored form. And in fact, if we can figure out what to divide a polynomial by so that we get a remainder of 0, we were able to get it into factored form by writing it as the product of the divisor and the quotient. So the whole point of today's lesson is going to be, given a polynomial, get it into factored form. So we have to figure out, well, what can we divide it by so that it'll have a remainder of 0? And there's a couple rules that'll help you figure out what you should divide it by so that you get a remainder of 0 and can get it into factored form. So let's get started with the first rule, which is called the factor theorem. It says x minus b is a factor of the polynomial if p at b equals 0, which means if it has a remainder of 0. Similarly, ax minus b is a factor of the polynomial if p at b over a equals 0. This is just a way of saying if the 0 of the divisor, whether it's of that form or that form, makes the dividend be 0, we know the divisor is a factor of the dividend. That's the factor theorem. Example 1 says determine if x minus 3 and x plus 2 are factors of this polynomial. They would be factors of that polynomial if I were to do the division of that divided by either of these and get a remainder of 0, I know they would be factors of it. But we don't actually have to do the division. We can just use the remainder theorem. Plug the 0 of the divisor, so what makes x minus 3 be 0 would be 3. Plug that into the polynomial function. If it makes the function be 0, then we know it is a factor. So I'll plug 3 in for all the x's. And then I'll evaluate this. So I have 27 minus 9 minus 42 plus 24. And this, in fact, is 0. So since the remainder is 0, we know x minus 3 divides evenly into p at x. right? It would have a remainder of 0. So that means that x minus 3 is a factor of the polynomial. Is x plus 2 a factor? Well, we'd have to plug the 0 of x plus 2, which is negative 2, into the polynomial. So we'll evaluate p at negative 2. So it would be negative 2 cubed minus negative 2 squared minus 14 times negative 2 plus 24. And we'll evaluate this and see what we get. We would get negative 8 minus 4 plus 28 plus 24. I can tell this isn't going to be 0. And in fact, it is 40. But the fact that it's not 0, right? Since the remainder is not 0, we have figured out that x plus 2 does not divide evenly into the polynomial. So x plus 2 is not a factor of the polynomial. So if we are trying to factor a polynomial, basically what we need to do, we need to figure out what do we divide it by. So we need to quickly test values to see what would make the polynomial be 0. Once we find that, we know what we should divide the function by so that we can get it into factored form. In this section, the polynomial that we're dividing is always going to have a leading coefficient of 1. That's the easier format, so let's start off with that. So for example, this is the first one we're going to do, just so you can visualize it. Notice the leading coefficient is 1. We're going to try and factor that. Now, it doesn't tell you what to divide this by to factor it. So we could just randomly guess values to plug in and see if we can eventually find something that makes it be 0. Or we can use something called the integral zero theorem to help us figure it out. The integral zero theorem tells us basically if there are integers that will make the polynomial be 0, those integers are going to be factors of the constant term of the polynomial. So for this one, for example, the constant term is negative 6. The integral zero theorem tells us if there are integers that make it be 0, those integers will be factors of negative 6. So we just have to test factors of negative 6. So that could be plus or minus 1, 2, 3, or 6. So the positive or negative of any of those are the integers that could make this be 0. Now maybe none of them make it be 0. As many as 3 of them could work because this is degree 3. A degree 3 could have 3 x-intercepts, so 3 zeros. But we just need to now test any of these until we find just one of them that works. It doesn't matter which one we find, we'll still be able to get to the same final factored form answer as long as we do our division properly after we find a 0 of the polynomial. I would always recommend just try 1 first. Why not? 1's easiest. So plug 1 into the function. So we would get 1 cubed, 2 times 1 squared, minus 5 times 1, minus 6. Is this 0? That's what we're interested in. So it'd be 1 plus 2 is 3, minus 5 is negative 2, minus 6 is negative 8. Okay, it's not 0. So since p at 1 does not equal 0, we know that, well, what factor would have a 0 of 1? The x minus 1. So we know that, okay, x minus 1 is not a factor of p at x. So let's not divide this function by x minus 1 because it doesn't divide evenly into it. It has a remainder of negative 8. So let's try another one of these integers. How about 2? So we would have 2 cubed plus 2 times 2 squared minus 5 times 2 minus 6. And here we would have 8 plus 8 minus 10 minus 6. Hey, that's 0. So since p at 2 equals 0, we know that the factor that would have 2 as its 0, so x minus 2, is a factor of the polynomial. It divides in evenly. It's got a remainder of 0. So what we now do is we divide the polynomial by x minus 2, and then we can write it in factored form. And we can do the division using long division or synthetic. It's up to you. But since the divisor that we're going to use is degree 1 leading coefficient 1, I think synthetic is a lot easier. So I'm not going to do long division. I'm just going to do the synthetic division. So I'm going to set up my table. And in the table, the 0 of the divisor goes here. And we figured out the divisor is x minus 2. The 0 of that is 2. So I put that here. And then the coefficients of the dividend, the polynomial, go across the top. So 1, 2, negative 5, negative 6. 1, 2, negative 5, negative 6. And now I'll do the synthetic division. Bring it down. 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. Negative 5 plus 8 is 3. 2 times 3 is 6. And negative 6 plus 6, good, we got 0. If we didn't get 0 for the remainder, we would know something has gone wrong somewhere. So our remainder is 0. Perfect. 3 is the coefficient of the constant term. 4 is the coefficient of x. 1 is the coefficient of x squared. So what I can do now, since I've done the division and got the remainder of 0, I can express the original polynomial, so the x cubed plus 2x squared minus 5x minus 6. I can express that as a product of the divisor, which we had to figure out on our own, multiplied by the quotient. So we now have it in factored form. That's not fully simplified factored form though, because this quadratic can factor further, so we'll factor it further. There are numbers that multiply to 3 and add to 4, and those numbers are 3 and 1. There we go, the original polynomial. This is the fully factored form, x minus 2 times x plus 3 times x plus 1. And you should notice from that fully factored form that there were 3 integers that would have made the polynomial be 0. 2, which is the one we found, but also negative 3 and negative 1 would have worked as well. So in this list here, 3 of those numbers would have worked. It didn't matter which one we found, we just had to find one that worked, divide by the corresponding factor, and then we can get it into fully factored form. Let's try another one where we are factoring a polynomial with a leading coefficient of 1. So if I want to factor this, I'm going to have to figure out something that makes it be 0. And the integral zero theorem tells us that if there are integers that work, they will be factors of negative 18. So what are factors of negative 18? It would be plus or minus 1, 2, 3, 6, 9, or 18. So there are 12 numbers here, right? The positive or the negative of any of those numbers. We just have to find one number that works. So I'm going to get Desmos to test some of these values for me. So I would try 1 first. Nope, that didn't work. How about 2? Nope, didn't work. How about negative 1? Yep, negative 1 works. And maybe some more numbers would work. Now this is a degree 4 function. Up to 4 of these could work. Maybe negative 2 also works. Hey, negative 2 also worked. Maybe negative 3. Hey, negative 3 also works. And 3 also worked. Hey, I found all 4 that work. I can technically write this in factored form now. But let's go through the process algebraically. The point is, we find a number that works. So you would write down any tests that you did. We tried p at 1 first and got negative 48. Okay, therefore x minus 1 is not a factor. And I think we also tried p at 2. I'm not going to bother writing that one, but we also tried p at negative 1. We figured, hey, that's 0. Therefore, x plus 1 is a factor. So we do some tests, we find an integer that works, and then the corresponding factor that has that integer as its 0 is a factor of the polynomial. Oh, and I have this sentence written here for us as well. So since p at negative 1 equals 0, this tells us that x plus 1 is a factor. So let's actually use division to determine the other factor. So let's find the quotient we get when we divide the polynomial by x plus 1. And once again, this divisor is degree 1, leading coefficient of 1. Synthetic division is the easiest thing to do. So I'll set up my synthetic division table. The 0 of the divisor goes here. And the dividend, I have to put the coefficients here. Now, is the dividend missing any terms? It has degree 4, 3, 2, 1, 0. Nope, it's got all of them. They're in the proper order, so I can write the coefficients. 1, 3, negative 7, negative 27, negative 18. And let me do the synthetic. Bring the first term down. Let me put my operator symbols. Negative 1 times 1 is negative 1. Add, I get 2. Negative 1 times 2 is negative 2. Add, I get negative 9. Multiply, 9. Add, get negative 18. Multiply, get 18. And add, get 0. So this is my remainder. And here are the coefficients of the quotient. The degree 0, the degree 1, the degree 2, and the degree 3 term. So now I can rewrite the original polynomial x to the 4 plus 3x cubed minus 7x squared minus 27x minus 18, I can rewrite that as a product of, so this is equal to, a product of the divisor, x plus 1, times the quotient, x cubed plus 2x squared minus 9x minus 18. This is factored form, but it's not fully simplified factored form. This factor is degree 3. Maybe that factors further. And to factor that further, there's actually two options. We could do this whole test for zeros and do synthetic division again, or there's a shortcut. Factoring by grouping actually will work for this, but we'll get to that in a second. Let's pretend you didn't see factoring by grouping would work, and we go ahead and do a whole nother round of synthetic division. So what we would do is, I just copy and pasted what we have so far down here. What we would do is, we would, off to the side, see if we can factor this further. So I would need to first figure out what the possible zeros of that are. So I will write possible zeros, and the possible zeros are factors of the constant term. So plus or minus 1, 2, 3, 6, 9, or 18. Okay, so now what I have to do is I have to test which of those values will make this be 0. So once again, I'm going to get Desmos to test for me. Okay, so I rewrote that function there, and let's try those factors of 18. So we could try 1. No, 1 doesn't work. How about negative 1? Negative 1 doesn't work. How about 2? 2 doesn't work. How about negative 2? Hey, negative 2 works. In our tests, we figured out f at negative 2, and we can call this function whatever we want. I'll call it function f at x. So f at negative 2 is 0. What does that tell me? It tells me that x plus 2 is a factor. So I can do a synthetic division where I divide this factor by x plus 2. So I'll put the 0 of the divisor here, so negative 2, and then the coefficients of that across the top. And it has degree 3, 2, 1, 0. It's not missing any terms, so I'll just write the coefficients, 1, 2, negative 9, negative 18. Bring down the 1. Negative 2 times 1 is negative 2. Add, I get 0. Multiply, I get 0. Add, I get negative 9. Multiply, I get 18. Add, I get 0. Good, I got a remainder of 0. That means I've done it right. There's my x to the 0, my x to the 1, and my x squared term. So we just figured out that I can rewrite that factor as a product of the divisor times the quotient. And don't forget to leave this x plus 1 here. I can rewrite this part of it as a product of x plus 2, that was what I divided it by, times the quotient, which I got x squared minus 9. And hey, that's a difference of squares. I could factor that further. X squared minus 9 would factor to x minus 3 times x plus 3. There we go. There's the full factored form. And from the factored form, notice that negative 1, negative 2, 3, and negative 3 all would have made the original polynomial 0. So an alternate method for this question, once we were at the step where we had done the first round of division, and I got it into this factored form, where I had it as x plus 1 times this quotient, we didn't actually have to do synthetic division again. For this specific example, there was actually a shortcut that would have worked. Let's look closely just at this factor. That's the one that we had to factor further. If I had have done factoring by grouping, I could have avoided having to do synthetic division again. I could have just grouped the first two terms together, so x cubed plus 2x squared, group those together, plus group the negative 9x minus 18 together, and then common factor from each group, take an x squared from the first group, and I would have x plus 2. Take a negative 9 from the second group, and you would have x plus 2. And notice we have a common binomial. They both have an x plus 2. So we could common factor out that x plus 2 and get x squared minus 9, which factors to x plus 2 times x minus 3 times x plus 3. So we could have replaced this with this by doing factoring by grouping, which would get us to the exact same final answer of, don't forget that factor of x plus 1 times the three factors that make up that x cubed function. X plus 2, x minus 3, x plus 3. We could have got the same answer, but that was a lot faster. If you have 4 terms in a factor, try factoring by grouping. See if it works. Take a common factor from the first 2, take a common factor from the last 2, and see if you get a common binomial. If you do, factoring by grouping works, do that. Okay, example 4 I put in here just to show you another time when factoring by grouping could work. There are a lot of long ways to factor this polynomial, but the fastest way would be to do factoring by grouping. Before you do anything, you should always check and see, is there a common factor? And in fact, all 4 of those terms have an x. So let me just take out an x to begin with. And then in brackets, I've got x cubed minus 6x squared plus 2x minus 12. Okay, now this polynomial in brackets, that factor, it has 4 terms. 1, 2, 3, 4. Whenever there's 4 terms and you want to factor it, try factoring by grouping. It's not always going to work, but it might, and it might save you a ton of time instead of testing for zeros and doing synthetic. So when I say see if grouping works, I mean from the first 2 terms, take out a common factor. So take out an x squared from the first 2 terms and divide those first 2 terms by x squared. I'd get x minus 6. From the last 2 terms, take out a common factor, so I could take out a 2, divide them both by 2, and I get x minus 6 again. The fact that these are the same means factoring by grouping works. So I could common factor out that common binomial of x minus 6, and if I do that, I'm left with x squared plus 2. We got that entire degree 4 polynomial into fully factored form without having to do any testing for zeros or synthetic division. So if there's 4 terms, check if grouping works. In the last section of this lesson, you're going to learn how to factor polynomials that have a leading coefficient that is not 1. Now the process is relatively the same, it's just instead of the integral zero theorem, we are going to look at something called the rational zero theorem. So when testing values to see numbers that could make the polynomial be 0, we don't only test integers, we're going to test some fractions as well. And what fractions are we going to test? Well, here's the rule. Suppose p at x is a polynomial function with integer coefficients, and x equals b over a is a 0 of the polynomial. Well, to get that b over a, we know that b would be a factor of the constant term, and a would be a factor of the leading coefficient. So for example, for this one, the constant term is 2, so we'll call that b. Factors of that are plus or minus 1 or 2. And the leading coefficient, 3, we'll call that a. The factors of that are plus or minus 1 or 3. The fractions that could make this polynomial be 0 are factors of the constant term divided by factors of the leading coefficient. So I just have to do each of these values for b divided by each of these values for a. So I'll start by doing 1 divided by 1 and 3. And that would give me plus or minus 1 over 1 and 1 over 3. And then I'll do 2 divided by 1 and 3. So that would give me 2 over 1 and 2 over 3. And keep in mind, it's plus or minus of any of those. So there's actually 8 numbers there. So just to summarize it, the possible numbers that could make this polynomial be 0 are factors of the constant term divided by factors of the leading coefficient. So when the leading coefficient is not 1, that's when we get these fractions that we also need to test. So now what we have to do is, we have to figure, well, which one of these 8 numbers, and up to 3 of them could work, because this is degree 3, but we need to find one of these that makes the polynomial be 0. If we can find one that is 0, that will allow us to figure out what to divide this by so that we can get it into factored form, because that is the goal of this question, is to factor it. I would test the integers first before I tested fractions, but it's up to you. I'm going to test 1 first, so if I plugged 1 into this equation for x, would it make it be 0? I'd have 5 minus 7 is negative 2, 8, plus 2 is 0. It does work. P at 1 equals 0. So since P at 1 equals 0, that tells me that x minus 1 is a factor of p at x. So what I need to do is divide the p at x function by x minus 1, and then I'll be able to get it into factored form. And since this divisor is degree 1, leading coefficient 1, synthetic division works. So let me do synthetic division. So the polynomial is 3x cubed plus 2x squared minus 7x plus 2. And I'm now going to be dividing that by x minus 1. So I'll do that off to the side. The 0 of the divisor is 1. The coefficients of the polynomial go across the top, and it has degree 3, 2, 1, 0. So they're all represented. So I can put all the coefficients in order, 3, 2, negative 7, 2. And now I'll do the synthetic. Bring the first term down, multiply it by 1, add, I get 5, multiply, I get 5, add, I get negative 2, multiply, I get negative 2, add, I get 0. So keep in mind that 0 is the remainder. That's good. That means we've done it properly. And these are the coefficients of the quotient. So I can rewrite this polynomial in factored form. I can rewrite it as a product of the divisor and the quotient. And this second factor, this quadratic, I should see if it factors further. Are there numbers that multiply to negative 6 and have a sum of 5? So I'm looking for a product of negative 6 and a sum of 5. So the numbers that work would be 6 and negative 1. So what do I do with those numbers? Since the coefficient here is not 1, I have to factor this by grouping. So I'm going to split the middle term, the 5x, into 6x minus 1x, because 6 and negative 1 are the numbers that satisfy the product and sum. And then what I do is I factor this by grouping by taking a common factor from the first two terms, so a 3x, and that gives me x plus 2 when I divide it by 3x. And then take a common factor from the last two terms, so take it a negative 1. And look, I get that common binomial of x plus 2, so I can common factor out that common binomial of x plus 2, and that leaves me with my last factor of 3x minus 1. So there we go. That polynomial has now been fully factored. Last example. We're going to factor this polynomial and this polynomial has a leading coefficient that is not 1. So when I test for zeros, I have to test factors of the constant term, so plus or minus 1, 2, 3, or 6, divided by factors of the leading coefficient, so plus or minus 1 or 2. So the fractions that could be zeros of this polynomial are each of those numbers divided by each of those numbers. So plus or minus, let me do 1 over 1 and 1 over 2. So that gives me 1 and 1 over 2. Now 2 over 1 and 2 over 2. So that's 2, and 2 over 2 is 1, and I already have that. Then 3 over 1 and 3 over 2. Then 6 over 1 and 6 over 2. But 6 over 2 is 3, and I've already got that. So here's my complete list of 12 numbers that could make this be 0. Up to 3 of them could work. Let's find one that works. So let's do a test. So hopefully 1 works. Let's just try 1 first. 1 would not work. Maybe negative 1 would work. If I evaluate p at negative 1, does it work? Oh, I'd have 2 times negative 1 cubed plus negative 1 squared minus 7 times negative 1 minus 6. That would be negative 2 plus 1 plus 7 minus 6. Hey, that works. That's 0. Negative 1 plus 7 minus 6, 0. So what does that tell me? Therefore, x plus 1 is a factor. So this original polynomial, I'm going to divide it by x plus 1. So the original polynomial, let me rewrite it. P at x equals 2x cubed plus x squared minus 7x minus 6. That original polynomial, if I divide it by x plus 1, I should get a remainder of 0. So let's do that off to the side. Let me divide this by x plus 1. So I put the 0 of the divisor here. The coefficients of this polynomial go across the top, and I have degree 3, 2, 1, and 0. So I don't need any 0 placeholders. So I'll just write 2, 1, negative 7, negative 6. And now I'll do the synthetic division. Bring the 2 down, multiply it by negative 1. 1 plus negative 2 is negative 1. Multiply that by negative 1. Negative 7 plus 1 is negative 6. Multiply that by negative 1. And then my final addition, I get 0. Good, a remainder of 0 means we did it properly. And here's the coefficients of the x to the 0, the x to the 1, and the x squared. So this original polynomial, I can rewrite it as a product of the divisor and the quotient. And once again, this second factor is degree 2, so we should check if it factors further. We should look, are there numbers that have a product of negative 12 and a sum of negative 1? And there are. Those numbers are negative 4 and 3. So I should split the middle term into negative 4x plus 3x, and then factor that by grouping. Take a common factor from the first two terms. I would take out a 2x and get x minus 2. Take a common factor from the last two terms, so take out a 3, and I get that common binomial of x minus 2. So I can common factor out the common binomial, and my final factored form would be x plus 1 times x minus 2 times 2x plus 3. And there we go, it's been fully factored. So for this lesson, make sure you now go try the practice problems. Factoring polynomials is going to be very important as you move forward in your math career. So give those practice questions a try, and that's it.